have a little bit of a relatively short number theory proposition I'd like to show you guys. Now this reads 2 raised to the b plus 1 divides 2 raised to the ab plus 1. Now we are assuming that a and b are positive integers or non-negative integers, I guess. So we'll write down a and b are understood to be integers greater than or equal to 0. And that's the stuff of number theory. You're studying the integers. Okay, so that much is true. We're also given that a is odd. Now, just a little bit of, some people aren't that familiar with this notation, but just an example, a numerical example, 3 divides 12 can be rewritten in a congruential form. In other words, 3 certainly divides 12 because 12 is equal to 4 times 3. But that's equivalent to just saying that 12 is congruent to 0. 12 is congruent to 0 mod 3. Okay, let me get this going here. Okay, so this is the same thing as saying 12 leaves a remainder of 0. Or you can say 12 is congruent to 0 mod 3. All right. Now that comes in, that formulation of the divides operator comes in pretty handy here. We finish this mod 3. Now, so it turns out we can rewrite this expression that we're trying to prove in its equivalent congruence formulation. Okay, and it turns out you can treat these congruences very much like regular equations. And so if we subtract 1 from both sides, we get this statement. So what I'm telling you is that if we can prove this right here, we will have proved this. All right. So that's often the way a proof goes. You rewrite it in a formulation that's slightly easier to manipulate. Now, so we have this going on. Now also, this right here would be trivial, right? This statement right here, 2 raised to the b plus 1 is congruent to 0 mod 2 raised to the b plus 1. That's just think 3 is congruent to 0 mod 3. 5 is congruent to 0 mod 5. So that's all this is saying. And then when we subtract 1 from both sides, we get this. Okay? Now the very next step to get us back to this statement right here is to exponentiate both sides. And again, you're treating this congruence just like it's an equality. We raise both sides to the a power. Now you may notice right here, since a is odd right here, if you raise a negative 1 to an odd power, you're going to get negative 1 back. Let's take a look at that. So in other words, we can rewrite this as 2 properties of exponents, and we'll just write it in alphabetical order. That's kind of convenient. 2 to the ab, all right, is congruent to negative 1. Okay, y'all, it's understood this is the modulus, so I won't rewrite that. And y'all, that's because this a is stipulated as being odd, right? So we've completed the proof, actually. We've completed the proof. It was fairly short. You could do it by long division also. It's a little more tedious that way. But again, the idea there is like if you have minus 1 raised to the 5th power, you know that they're going to cancel out pairwise, right? And leave a negative 1. Okay, so minus 1 raised to the 5th power is equal to negative 1. Okay, now let's just go ahead and go down and work a concrete example here. And y'all, by the way, we are done with the proof right here at this stage of the problem because 2 to the AB is congruent to negative 1, and that's what we set out to prove. Now, let's just go ahead and look at a concrete example. Let's say we had 2, let's do 2, maybe, I'm just trying to think of some numbers that are relatively manageable. Let's try 2 to the 3 times 4 maybe. think I can keep track of that. 2 to the 3 times 4. So you can see the 3 would be the odd. Okay. And then we'll do plus 1. Okay, and then let me write it over. Because what we just proved, this has to be an integer, this quotient I'm about to write down. So this would be 2 to the 4th plus 1. And y'all, just to be clear on that, this is the 2 to the b dividing the 2ab. And let me just back up just to be sure I'm not. Okay. The way this is written, it's just kind of sideways, but this is your 2 to the b plus 1 divides 2 to the ab plus 1. And that means that would resolve to an integer if you actually did the division. Okay, so let's take a look at what this ends up being. Now, so this would be, now y'all, I'm just going to go ahead, we could do this by hand if we had to, but I'll go ahead and pull out the calculator on this, folks. You end up with 4,097 in the numerator. $4,097, and then downstairs we can do that in our head. 2 to the 4th is 16 plus 1 is 17. All right. Now again, this is something that would be very tedious to show manually, or it's not a whole lot of fun, but that does resolve to an integer. All right, which says that this special case is exactly what we set out to prove, that 17 divides 4,097. Here's the proof. And then that's exactly in this form, 2 to the AB, where A is odd. Okay. And then this right here, of course, is B, 2 to the B. Okay, folks, hope you like that. It's just a fairly quick number theory proposition.